This is the lecture for regular psychology on perception. This lecture was given on Thursday, November 19th. When we talk about perception, we're talking about how the brain interprets sensory signals. When we talk about auditory perception, there are three aspects of perception that play a role in how we experience sound and how our brain organizes and perceives sound. For the volume, it's based on the intensity of the sound wave. The more intense of a sound wave, the further it's going to travel along air molecules, and the closer you are to the impact, the more intense that sound wave will be. For pitch, it's definitely a little bit more complicated. For pitch, we have different hair cells in our cochlea, the snail shell shaped structure of the inner ear. And those hair cells all correspond to different pitches. So as the fluid in the cochlea moves around based on the sound waves that are causing the movement of the eardrum and the small bones in the middle ear, when that fluid moves around and it stimulates a specific hair cell, that hair cell in turn stimulates a specific nerve. That specific nerve corresponds to a different pitch. So certain hair cells and certain nerves correspond to high pitch sounds, and certain hair cells and different nerves correspond to lower pitch sounds. When talking about location, the way that it works is that the sound waves are going to be, when we're talking about a sound source that is on one side of you, the sound wave will be more intense in one ear, closer to the sound's original source, than it is in the other. The other has to have the sound wave travel around the head, around what we would call a sound shadow, and enter into the other ear, the opposite ear, but with slightly less intensity. And because we can perceive the differences in the intensity of the sound wave, we can perceive that the location is coming from the side in which the sound is more intense. When talking about visual perception, in our previous lecture on vision, we talked about how there are four parts of vision that our brain sees, that our brain puts together, which are shape and form, color, depth, and motion. Now, for shape and form and color, we're talking about our rods and cones. The rods allow us to perceive shape in black and white, while the cones allow us to perceive detail and color. But the other aspects of vision are a little bit more complicated in terms of how we perceive them. Depth perception is the idea that what we are seeing we know to be in three dimensions. Whereas the image that our eye takes in is really just two-dimensional, like a camera photograph. In truth, our brain knows that there is depth, that there is that third dimension, not just height and width, but also depth. That certain things are closer to us and other things are further away, despite the fact that our brain is just looking at a two-dimensional picture. So what does this? Well, it depends on whether those things that are close, whether those things that we're looking to perceive depth are close to us or from far away. Binocular cues are ways that we perceive depth at close distances. To do this, we need to use both eyes, which is why we get the name binocular cues. One way that we do this is something called binocular convergence. When things are really close to us, what we do is we have to turn our eyes inward to see it. This movement of the eyes and stimulation of the muscles that move the eyes tells our brain that what it is we're looking at is close to us. Now, if you wanted to do a nice trick about this, is to see how binocular convergence works, is to make the floating finger sausage. To do that, take two fingers, hold them about an inch apart at about arm's length, and slowly bring them towards your eyes. But instead of focusing on your fingers, focus on something behind your fingers, like a wall or a window or a computer or something. And you will then see eventually that image will kind of go into two images where you will then see kind of the mixture of those two images be that floating finger sausage. But then when we focus our vision on those fingers, we can see that it's just two fingers again. And in doing that, we're making ourselves temporarily cross-eyed, and the movement of those muscles, the convergence of our eyes, and the movement of those muscles tells our brain that what we're seeing is close in front of us. The other binocular cue is something called retinal disparity, and that's for perceiving depth at close distances, but slightly further away than binocular convergence. With retinal disparity, this is the idea that each eye sees a slightly different image independently from one another. And you can kind of test this out by closing one eye and then opening it. And then when you open it, close the other eye, kind of making like a camera one, camera two. You'll see the image that your brain is perceiving kind of move side to side when you do that. Now, we can also perceive depth at far distances, and this is through the use of monocular cues. Monocular cues are ways to perceive depth at far distances, and each eye can do this independently. And these are more visual cues than actual characteristics of the eye. And I'll come back to this slide, but I'll just show you some monocular cues. So monocular cues like relative size, in which the thing that's closer is bigger, or linear perspective, where things that are closer are wider and get narrower as they go off into the distance. Or the fact that some images will be in front of one another, or that things sometimes in the foreground will be more detailed. All of these give us cues that we're seeing things further away and other things we're seeing closer. When we perceive motion, it's our brain interpreting individual images, one after another after another. Our brain can interpret 48 images every second. And what our eyes are doing are sending the individual images. Our brain is essentially smoothing them out so that we can perceive motion. Kind of if you think about like a flip book that you might have made in elementary school, that flip book of a stick figure doing something is a bunch of individual images, but when you flip it all together, it makes the stick figure move. Ultimately, when all of our senses take in all the stimuli in a given moment, our brain has to interpret all of that so that we can understand the world around us. This is known as a perceptual set. And a perceptual set is essentially just the overall kind of every stimulus that our brain is taking in that moment so that we can then understand reality. Most of the time, our perceptual sets are correct, but sometimes they can be fooled. Sometimes our perceptual sets can create illusions. Expectation is one of those things that can create that illusion. If we expect to see something, then there is a stronger chance for us perceiving it, even if what it is isn't necessarily there. For example, if you expect that aliens are real or that there is a Loch Ness monster, when you see these pictures, you may have a higher chance of perceiving it as UFOs and the Loch Ness monster rather than some clouds and a piece of wood in the lake. Context is another way that we alter our perceptual sets. Sometimes when we see things in context with another, it makes us perceive it incorrectly. For example, the player in yellow is 6'8", even though he looks like he's maybe 5 feet tall. And that's because the player in blue is 7'9". And so in context, he obviously looks a lot shorter, but compared to any one of us, he'd probably tower over all of us. Which leads me to the question, is the man inside or outside the house? This illusion is designed to mess with your perceptual sets by having your expectations of how you see images of inside the house or outside the house, or seeing the porch and the man doing the writing in context with the walls, or and whether or not we expect those walls to be inside the house or outside, and so on. It's meant to make it so that we don't interpret it correctly. Another aspect of perception that does need to be discussed is something called Gestalt psychology. This is one of the oldest forms of psychology, and it originated in Germany. And in German, Gestalt means form. It's a loose translation. One of the ways that we can interpret a form is by interpreting the differences between a figure and a ground. Now, the ground is always the background of what we're seeing, where the figure is what we're seeing in the front. If you see Guys walking downstairs here, they are the figures, and the white background is the ground. And yet, if you see arrows going left and right, then those arrows would be the figure, and the black background would be the ground. We also tend to create forms by automatically creating unconscious groupings. One of those groupings being figure versus ground, but other ways that we naturally group and create forms is through connections between things. Sometimes, if things are close together or close in proximity, we tend to group it together. If you take a look at the image in the top left, you might perceive 3 sets of 2 lines rather than 6 individual ones because each set of 2 is closer to one another. Another way that we group together is similarity. When you look at the image in the top right, you'll see that probably a column of triangles, a column of circles, and a column of triangles rather than 9 individual shapes because we group them together by similar shape. We also group things together when they are continuous. We make continuous lines out of things that may not be continuous. Rather than see line segments in half circles, we see a squiggly line intersected by a horizontal one because our brain naturally groups all those different curved segments together. And finally, connectedness. We tend to group things together that appear to be connected. There could even be spaces between the lines and those black dots in the bottom right, and we would still probably perceive it to be connected. Finally, our brain does to do something to make sure that we're not freaking out every time we change the angle of what we're seeing. This is known as perceptual constancy. It doesn't just apply to shape and size, but it also applies to things like brightness and color. And what perceptual constancy is the idea that our brain, even though we see things from different angles or we see things from different brightnesses, we know that the colors are the same, that the shapes are the same, that the size are the same, that the brightness is the same. When you look at a door that's closed and it's a rectangle, and then you open the door, your eyes are perceiving some sort of weird parallelogram, but your brain still perceives it as a rectangle because the brain keeps the shape constant even though the eyes are seeing a different angle. When we see a person closer and a person far away, we know that those two people are probably generally the same size, just the one that's further away looks smaller because they are further away. With color and brightness, it works the same way. Different amounts of light can create different shades of color, even if the colors are the same. All the yellow dots, all the blue dots are all the same color in this image. Even though our eyes see different colors, our brain knows that it's just different way the angles are hitting, the light is hitting the angles of the cube. Which leads me to the question, what color is the dress? Now, many people see white and gold, while others see black and blue. And this really comes down to brightness constancy here, plus some messing with our perceptual set. Behind the dress, it is distorted. It's overly bright. We can't make an expectation of how much brightness is in the room based on the context of what's going on behind that dress. So instead, we just have to use our own expectations of what we think might be happening here to allow us to perceive it. Ultimately, people who see it as white and gold probably see this in very high levels of light, in that the high level of light is, or in low levels of light, and this low level of light is shading out the whiteness and it's darkening the gold. But in truth, the dress is black and blue. In truth, what's occurring is that we're seeing this dress in high levels of light. And the problem is for people who are seeing it as white and gold, their expectations of what kind of lighting is in the room is affecting how they're seeing the dress overall. And so when we make the lighting darker and you can kind of see behind the dress that makes it a normal brightness, you can see that darkens the dress even further to make it more black and blue. The dress, by the way, is originally black and blue. And that is the end of the lecture.